Welcome back to Parallel C++ for scientific applications. I'm very glad that you're still showing up. It's always nice to see that students are interested for one reason or another. Before we start the midterm, I will take down today. So if you still haven't submitted the midterm, your work on the midterm, please do so before midnight today, because I will remove the instructions and I will block submission after that day. Last time we talked, actually last two lectures, we talked about data parallelism, and I introduced you to a way of thinking about parallelism in terms of whole sequences, in terms of applying certain steps to all elements to a sequence. And as we have seen, there is a whole list of existing algorithms that can help with that. And these algorithms are essentially building blocks you can combine in various ways to achieve the results you're interested in. What we will do today and next lecture on Thursday is I will talk about task-based parallelism and concurrency in general. And we will see that this is a completely different approach to thinking about parallelism, because it introduces a concept that is called asynchrony, which will help us in many ways to write code in a way that is easier to reason about, and B, to write code that is giving us better performance because it helps us utilizing the resources we have in a better way. And last but not least, as we will see, this is kind of a parallelism that lends itself very well to distributed computing. And we will start talking about distributed computing on big machines next week or the week after, depending on how things play out. Asynchrony and task-based parallelism is some method of approaching distributed computing that allows to extend everything we learned to the distributed case without complicating things too much. At least I hope so. Okay, let's get going with today's lecture then. So task-based parallelism is a programming model that focuses on distributing tasks and executing those concurrently. Concurrently by different processes in the distributed case, or by different threads in the shared memory case. Task parallelism is distinguished by running many different things at the same time. In data parallelism, we always said, okay, we apply the same operation on all elements of our sequences, so all the tasks we have created were executing the same code in parallel. Here we extend that by saying tasks can do that. They can run possibly completely unrelated tasks concurrently. That can happen on the same data, as we will see some examples, but it can happen that these tasks operate on completely independent data that just happen to be some tasks that needs to be performed in order to make progress. And if there's some compute resources available, and I know that I need to do some computation anyway, so why not do it right away if there's not anything this computation depends on? One example of task-based parallelism is pipelining, or in general chaining tasks, where you have many tasks that depend on each other and you chain them automatically so that they are executed in the right order. So you move a single set of data through a series of separate tasks where each task is executed independently of the others. The only thing that has to happen is that any subsequent task is launched only after the previous task has provided the results. So it's very much a matter of thinking of dependencies between tasks. What can I do? At which point can I start running a particular task, which of the preconditions have to be met for that task to be, so I can start running it. So it explicitly relies on dependencies between tasks, where these dependencies are represented by data or by results that are produced by some previous tasks. I showed that table before on the last week when we talked about data parallelism, just to give you some juxtaposition of where the differences between data parallelism and task parallelism actually is. And we discussed the left side, so let's talk about the right column today. As I said, for task-based parallelism, we perform different operations either on the same or on different data concurrently at the same time in parallel. It's very much based or enables asynchronous computing, and I will talk about that and will introduce that concept in more detail in a second. So let's leave it at that at this point. The amount of parallelism is proportional to the amount of independent tasks you have available. So which task can I run at this particular point in time? Again, based on which of the preconditions for the various tasks have been fulfilled, so I can start running them. And in the end, load balancing depends on the availability of hardware and depends on the availability of sophisticated scheduling algorithms, which make sure that these resources are utilized, the compute resources are utilized accordingly. Let's take a very simple example. We have some client, a web browser, and we have a server, which is a web server, for instance. And if you think about the client sending a request and the server serving that request, and it takes about t seconds or parts of a second to perform that request, then the overall amount of throughput we can achieve in that system is 1 over t, obviously, right? Because I have to wait for t seconds, for the server will be busy for t seconds before it can operate on the next request. If we, however, start parallelizing the service request on the server by saying, okay, for each of the requests, instead of directly serving the request, I just either launch a new thread or launch a new process, which then is responsible for serving the request. Then in the context from the standpoint of the server, this is an asynchronous operation. It just kicks off the operation and said, hey, you do it, I don't care about it. Eventually, in the end, you can come back to me and tell me when you're done, but I'm out of the picture. And that allows us, if we assume that the spawning of a thread takes much less time than serving the request. Let's say spawning a thread takes lowercase t, which is much smaller than the amount of time spent to serve the actual request, we achieve a much higher throughput rate, obviously, because now the server will be available after 1 over lowercase t to start serving the next request. So the overall throughput will be much higher. So again, a simple case of parallelism, but this time we think about it by, hey, we have to do this piece of work to do, let's do it. How does that map onto hardware? Well, we know that our hardware is multi-core hardware. We have many cores on modern architectures. So we can build a system where each of those separate service requests, each of those tasks is running on a separate core simultaneously, which allows us to run concurrently many paths in parallel, where that parallelism comes from, right? We have a lot of compute resources. We have a lot of independent tasks that can run independently. So let's schedule them and make sure they utilize the hardware in the best possible way. If you look at task-based parallelism from the standpoint of our workflow, how to solve parallelization problems, we have already seen a lot of examples for the decomposition step. In decomposition step, we always were thinking about what can we do to our problem to split it into smaller problems so that each of those problems could be run sequentially on a single core and run these different parts of our problem in parallel on different cores using different threads. Now, if we take a step back and start thinking about these parts of our problem as independent tasks, then we immediately get into the realm of how do we assign these things to cores. And if you think about that each of those tasks essentially runs on one of the cores, then this assignment is kind of straightforward and obvious. So again, task parallelism is a method of parallelization that fits very, very well into our way of decomposing the system, the problem into smaller steps, into coming up with a strategy of parallelizing things. And I will give you some examples of that today. Okay, so if you remember Amdahl's law, we said that we have a problem. And the problem is that if you want to parallelize applications efficiently, and we want to make sure that the application runs 10 times faster if we run it on 10 times the amount of compute resources, then we have to be able to parallelize essentially 100% of our application. Because as soon as we leave only a very small part of sequential code in our application, be it I/O, be it startup code, be it synchronization, whatever, the overall achievable, theoretically achievable parallelization or scaling is limited by that very small sequential piece in our code. So what we need to do, we need to find other ways that allow us to fully parallelize our applications and better utilize the hardware. So we want to avoid sequential pieces of execution by all means possible. So if you remember that scheme I showed you for join parallelism, you have essentially a for loop which is parallelized. At the beginning of the parallel region, you spawn off a bunch of threads, you start executing some useful work, and as it happens, there's never exactly the same amount of work for all the cores available. So it could be temperature differences on the chip that makes the operating system clock down some of the cores so that they run slower. It could be other algorithmic problems that cause that, like Mandelbrot, right? Each pixel requires different amount of computation, so you can't really evenly distribute the amount of work across cores easily. So what that leads to the effect that some cores are finished earlier and some cores are finished later with their piece of code. And that means that you have these sequential pieces of execution snuck behind your back into your code. And you can't do anything about it, because in the end you have to wait for all the threads to be finished with their work before you can continue doing things. So for join parallelism, as nice as it is and as easy it is to reason about it, it has that built-in disadvantage that it is not very helpful in terms of Amdahl's law. It will constrain your parallelism significantly if you're not able to really evenly utilize all the compute resources you have inside that parallel region. And task-based parallelism, as we will see, perhaps not this lecture, but next lecture, helps mitigating that effect. And we will see how that can be done. So our goals are, and that is what I will aim for these two lectures, is to create or introduce programming APIs, facilities, mostly in this lecture from the C++ standard. Next lecture, very much based on what HPX gives you in addition. Facilities that expose the asynchrony to the programmer in a manageable way, so that you don't have to break your brain when you want to build applications that use asynchrony. So what we want to do is we want to make data dependencies between tasks explicit in a way that you can hand it to the underlying system, and the underlying system will obey those data dependencies and will schedule the tasks accordingly without you having to do anything. You just say, okay, this task depends on these two, and then you give these three tasks to the runtime system, and the runtime system will run them in the correct order. And We want in the end to provide manageable paradigms for handling all of that parallelism to utilize our machines in the best possible way. For those of you who don't know, the big cars are buses. We might not have seen them in Baton Rouge, but this is happening. This is essentially a picture that's happening on your computer, right? So you have a lot of things in the flight, you have a lot of things happening, and there might be some problems in coordinating. There could be some contention here and there, and especially if the tasks have different sizes, you get to the point that it's very difficult to manage things correctly. Even more if you have some idiots around here who just make things even worse than everything else. But this is asynchrony. This is what's happening on your computer when you start using tasks really to the fullest. Okay, what do I propose to overcome these kind of problems? I propose to introduce an asynchronous programming model that goes beyond data parallelism, that gives you the means of writing asynchronous code, and we will see how that looks like in a moment, where the objects, the C++ objects, the representation of your data in your program interact using asynchronous function calls. So instead of just calling a member function, say, hey, give me the result, you kick off the operation, and at some point later you get the result in a completely independent way. And as I said, we will see how that works. That very well lends itself to remote operations, because just imagine you have 2 nodes in your compute system, and you want to fetch data from the other compute system. So you have to send a message, tell the other node, hey, give me that data, and that data comes back. But that might take, I don't know, milliseconds, because network is involved, especially when the internet is in between. So using these asynchronous function calls will help us to excuse me. Will help us to mitigate these latency effects we introduce by using networking. I will introduce a concept which is called future, a future, not the future, but a future. And those objects are used to represent data dependencies in asynchronous code. So it's special C++ objects, not only C++. Futures actually were introduced first in Java in the early 70s. Then everybody forgot about them. And later on, starting 2010, 11, C++ has, the standard has futures as part of the standard library. So they represent data dependencies in these asynchronous execution flows and data flow scenarios. What we will see next time is that we want to, if you have a distributed application that goes beyond a single process, either several processes on the same node that kind of collaborate, or processes that are running on different nodes of a supercomputer, when you program these applications, you still want to reason about the whole application as a single application. You don't want to have to think about that you are actually dealing with disparate memory spaces where you can't directly access a memory of the thing that sits on the other node, on the other end of the network. And HPX introduces what's called an active global address space, and you will see how that helps with task-based parallelism in the distributed case. So tasks operate on C++ objects, where the objects are possibly distributed across a system. The nice part of that is, again, HPX, is that when you write code against such a concept, against such a programming model, you don't distinguish anymore whether the target of your operation is actually on the same node as you issue the call, or whether it happens to be on a different node, which gives you a very nice equivalence of local and remote operation, which simplifies coding these kind of very complicated applications. I will introduce a technique which we call a futurization technique. Very interesting way of transforming code that turns sequential code into, by minimal changes, by the way, into code that automatically is seemingly automatically parallelized. So you take your sequential textbook algorithm, apply very minimal changes to it, and suddenly you have a fully parallelized application, which is really cool. And all of this is conforming to the standard C++ standard. So if you know the C++ standard, it's not difficult to apply everything you know to and get started with that asynchronous programming model. And I will talk about that today and next lecture extensively. Okay, so asynchronous tasks. The idea is, please stop thinking in terms of threads. Threads are evil. Don't reason in terms of threads. Start thinking in terms of what needs to be done, not how do you want to do things. Where a thread is an implementation concept that really just happens to be there to drive the parallelism, you don't want to reason about parallelism in terms of how things are being done. You want to think in terms of tasks, which is application-specific notion. It tells you, yeah, I want to do these steps, this step, this step, this step. And you don't care whether it's run on one thread, on different threads, on the same node, on different nodes. Doesn't matter. So these tasks can run concurrently with other tasks, given that they are not interdependent. So I can't run two tasks in parallel concurrently at the same time if one of those depends on the result of the other task, obviously. You might say, hey, Intel, the compiler provider, they tell us for 50 years that they can auto-parallelize code. You give it some code and they do automatic parallelization. They claim that. They have never achieved it over 50 years. And the reason is that this poor compiler that sees that code has to kind of look at the code from a very low level and has to understand what the programmer was actually thinking. It has to figure out what are the data dependencies of the different variables, what are the data dependencies between the different tasks in that program. And once it has reestablished that dependency tree of operations, it can start parallelizing things. Because when two things are independent, they can run in parallel. And if things depend, then some sequencing has to be applied. So there's a reason why Intel wasn't able to do that. And they will never be able to do that, I believe, because it's like, you know, a mechanic in the car shop standing underneath the car and trying to figure out what the driver is thinking. It's not possible, right? You see everything, but you don't know anything, essentially. So creating programming models that naturally allow to convey these data dependencies to the underlying system is one of the possible solutions. You write normal code that looks reasonably sequential, but as a side effect of executing that code, the dependencies between the tasks are conveyed to the underlying system. And then the system knows, okay, these tasks are independent, I can run them in parallel or concurrently, or I can't, I have to wait for this task to finish before I can start other things. And this is what task-based parallelism is all about. And I hope to give you some idea over today's lecture and next lecture to give you examples and some introduction how you can do that. So try not to reason about how to do things. Try to reason about what should I do? What needs to be done before this particular thing, and so on. So let's go back to some conventional programming where we have 3 compute steps. We compute p, we compute x, and then we use p and x to compute h. 3 computational steps, and they might be complicated and very involved. We don't care. But what we know is that sequential code essentially creates some implicit dependency tree, which tells us that h depends on p and x, and in order to compute h, I first have to get the results from p and x. But P and X are independent, so in theory I could run those in parallel, concurrently at the same time, and nothing would change. The semantics of the program wouldn't change. So what we see in sequential execution is that we just execute things one step at a time. We first compute P, then we compute X, and then we use the results to compute H in this case. So each function is called in the sequence as the code is written, and the code waits for the function to return to give you the result. And that's the natural picture we have in mind when we write code, right? We just give it a sequence of operations, and we assume that these operations are executed exactly in the sequence as we have written them. And that's what the pure Intel compiler has to come back to and has to say, okay, the program has said these things have to run, but what can I parallelize? Which of those things are independent? So what we have seen last time mostly is that using plain threads is making things complicated to understand, because it's complicated to return a value from a thread. We had to jump through all kind of hoops with references and global variables and race condition protection and whatnot to be able to coalesce the results of different threads. And as I said, it often requires additional thread safety measures that aggregate over many of those results that are collected from the threads. So what I will show you, that there are facilities that can be applied to overcome at least some of those limitations in certain contexts. So the idea is to create a mechanism that allows to directly access the return value from a thread. You run a function, you get something back. Why not run that function on a new thread and get the result back in the same way? It's much more natural than having to funnel in some return value into the thread function by reference or whatnot. Which, by the way, as a nice side effect, or no pun intended, allows us to write side effect-free functions that really do only certain operations based on the arguments they receive without looking at global data, which makes things race condition free by definition. So we will develop a model that minimizes the thread suspension and synchronization, which is important. Whenever you have to join with a thread, whenever you have to wait for a thread to finish, the waiting thread gets suspended, possibly, because you have to wait for the other thread to finish. And that creates context switching in the operating system. And context switching are very expensive. So we want to create a model that avoids context switching as much as possible. And especially next lecture, I will show you a technique that allows to do that, to essentially to get rid almost completely of context switches that are forced onto the operating system by the user code. So we can reduce overheads that way as well. Okay, so how can we do that? Welcome to the future of computation. Okay. Anybody has read the Hitchhiker's Guide Through the Galaxy? Anybody? The book? Douglas Adams, Hitchhiker's Guide Through the Galaxy? Nobody? You should read it. It's really one of the best books, especially when you really want to laugh while reading. It's one of those few books when you read it, you just have to laugh because it's hilarious. The idea is that some alien race wants to find out what is the answer to life, universe, and everything else. And they build a supercomputer that should figure that out. And they switch on the supercomputer and ask it, hey, what is the answer to life, universe, and everything else? And the computer thinks for a moment and says, hey, come back in 7.5 million years. It will take that long for me to compute that. So that alien race goes away and says, okay, let's wait for 7.5 million years. So how do we express that in computing, that notion? Well, we write a function which gives us a universal answer to life, universe, and everything else. As in the end turns out, that answer is 42. Okay? That's why everybody in computing knows that when you say 42, it's the answer to everything. And you will find many, many references to that 42 in your life. By the way, in I think in the 5th tome, Douglas Adams actually comes back to it and answers, if this is the answer, what is the question? Right? I will not spoil the fun. Please read it. The question is completely unexpected and doesn't seem to correspond to the answer. But anyway, so okay, we have a function which eventually will return the answer to life, universe, and everything else, which is, as we know from the literature now, is 42. But it will take 7.5 million years to do. So you don't want to block your thread to wait for that thing to happen. You want to go on with your life, you want to do other things while that computer is doing things. So you create that computer, which is, by the way, in the book called Deep Thought. You use a facility which is called Async, pass that function to Async, and say, hey, please launch a new thread, and give me a object which represents the result that will be eventually produced. It's not the result itself, but it's kind of a handle that represents the result that will be produced. That object is called a future, and in C++ you have to tell the future what type does it represent. Well, in this case it's an integer, obviously. So what async does, it launches the function, comes back right away, gives you that future, and that future will become ready, will receive the answer whenever the function has finished computing. So we are free to do other things for 7.5 million years while that function is being computing the result. And eventually, when we run out of patience, we say, okay, now give me the answer. So we use our future and say, hey, future.get, give me the answer. And two things can happen. Either the answer has been computed and has been delivered to the future, and the future has that answer, then get will immediately return to you and will give you the 42. Or the universal answer function has not finished computing yet, at which point that get function will suspend and will wait for it to arrive. So it will come back only once. Whenever get returns, it has the answer for you. Which is nice, because now we can stop thinking about threads. We can now start thinking about tasks. And whenever we need the result of that task, we just say, okay, give me the result. And either it suspends and waits, or it gives me the result when it's available. So, and this is a model we will build everything around for today's and next lecture, because that future object is very, very powerful, and we can do all the asynchrony with that, because this is asynchrony, right? We kick off a new computation, say, hey, do it. I don't care how you do it, when you do it, your thing. I do my own things in the meantime. And at a certain point, actually, I need it, because otherwise I can't make progress on my computation. So I ask the future, hey, give me the result. And the code looks very straightforward without you even seeing that a thread is involved, which is great. So a state future provides a mechanism to access the result of a asynchronous operation. It provides methods for synchronizing with the result without having to reason about threads. You're thinking about tasks. Do this task, give me the result. So what methods do we have on the future to do the synchronization? There are several of those. I want to quickly introduce them. Well, we have the get function. I already mentioned that, which suspends until the computation has finished, and then it returns the result of the function. There is future also has a wait function. If all you want is to wait for it, you don't need the result at this point. You just want to make sure that computation is finished, which will suspend and wait for the computation to finish. There's a wait for. If you want to say, okay, please wait at most for a second, and if it's not there yet, come back to me so I can do other things. So the result is returned if it's available, or otherwise it will come back with an error code and tell you, hey, I have timed out. The result is not here yet, but you told me to wait for a second only, so here you are. And there is wait until, if you want to specify a certain point in time, until it should wait. Both of them block the specified amount of time until that timeout has been reached or the result has become available, whichever comes first. And then you can use get to actually get the result. If we look at it from a schematic point, you can think about it that way. We have one locality, which could be one thread, which could be one node, where we have some thread running, which creates a future object and then suspends because it needs to wait for the result. So at this point, we call get on the future, which suspends the current thread, which frees up the core, because the core can now do other things, right? You wait for 7.5 million years, do something useful. At the same time, on a different locality, where a different locality could be another thread, could be another node, whatever, that function starts executing. And whenever that function is finished, it will deliver the result back to our future, which will make our initial thread resume, and will be, so the initial thread can return and can continue on its merry way. So if you think about it from a distance, it really enables transparent synchronization between a consumer and a producer, where the consumer is our thread that calls get, and the producer is that function that computes the 42, and it takes a long time to do that. But more importantly, it hides the notion of dealing with threads, because, well, there's no thread involved, right? All what we do is say, hey, do this asynchronously. And it might not even launch a new thread. It might just do that on the same thread. It's completely system dependent. We abstract ourselves from the notion of how things are being executed. We just tell it what to do. The absolute critical piece of that is, however, that a future represents a data dependency. It represents the result to be delivered by another task. And only when get returns, we can actually go to the next step in our computation, and we can be sure that things are there. So it represents a data dependency, which is the central benefit of it. And we will see how that enables us to tell the system what data dependencies between the tasks actually exist. It makes asynchrony manageable, okay. It allows for composition of several asynchronous operations, and we will see how that works next lecture. And, well, kind of in parentheses, what I call, it turns concurrency into parallelism. In my mind, concurrency is always difficult to reason about. Parallelism is easy to reason about. So it makes things that you can't reason about because they run chaotically, concurrently. You turn that into something you can start reasoning about, because it's really just parallelism. There's independent tasks and there's a dependency between those. So let's get back to our synchronous example, and let's turn that into asynchronous computing. So instead of computing P directly, we use async to launch P and as a task. We get back a future, and async comes back right away. Yeah? So it doesn't wait for P to be computed. It comes back right away, gives you that future that eventually will receive your result. Then we compute our X on the current thread, because we have nothing else to do. So why not just compute it? And at the point when we want to compute H, we have our X result because we have computed it, and we get the result from the first computation by calling get on the future. Parallel computing, because now X and P will run concurrently right away. And you didn't even have to tell it to run it concurrently, right? You just said, okay, I have two tasks. One you launch asynchronously, the other one I'll do myself, and then suddenly you have parallelism. The program is still executed line by line as before, but async returns right away, even if compute P has not been computed, has not finished running yet. It might take 7.5 million years, as we learned, right? So the return future that represents a result will be computed, that can be used to synchronize with any subsequent operations. And while we still suspend here, because f.get might suspend, and in the beginning I said I want to introduce you to a model where suspension is essentially not necessary, we will see in the next lecture how we can prevent that from happening. How can we avoid that suspension is happening in the first place? For now, let's stick with that model as it is. So in the buff code, P and X are being run concurrently if and only if compute resources are available, obviously, right? If you have a lot of other things running at the same time, then this might not run concurrently because the system might decide, hey, I have no core for you available. Let's do it whenever things kind of calm down. Another example is, just for the sake of it, it's a trivial example, which figures out whether a given number is a prime number. Well, the usual way to do that is just to try out all divisors from 2 to the square root of our number and figure out if any of those divisions actually are divide our number evenly. And if one of those i's divides our number evenly, that means that it's not a prime, obviously. If there's no number which divides it evenly, it's a prime number. You probably have solved this problem in many occasions before, so I'm not going to discuss it too much. But it might take a long time to compute that prime number, right? If you have a very large number, it might take a moment to try out all the divisors and see if they actually divide our number and whether it's a prime. So we just launch it asynchronously. We call async, call our function is prime, and please note that isPrime is now a function that receives an argument. So async allows you to specify additional arguments which are passed through to the function. So when the function eventually is executed, whatever you pass as additional arguments to async will be passed along to the function invocation. So you can easily pass additional input data to your task in a very natural way, in the same way as if we were calling that function directly. Well, and then you call get, and if it returns true, it's a prime, and if it's returning false, it's not a prime. So that's a very simple example for that. So as I said, async, the first argument is a function, could be a pointer, could be essentially any invocable C++ gives you, could be function object, could be lambda. And the second and any following arguments are passed along unchanged to the when the function is eventually invoked. Because note, async, while it comes back right away and gives you a future, it doesn't mean that it already has started the thread that runs the function. Starting the function might happen 10 seconds after async has actually returned. So nothing might happen for a long time. So the arguments you pass into async are stored somewhere, and when the thread starts, or the mechanism, the execution agent starts running that runs that function, these arguments are passed along to it. So as before, the return future can be used to wait for the result or to extract the result. The value eventually provided by the future is whatever function has returned. And that's the whole scheme, that's the whole magic that's happening. So it's fairly straightforward to understand what it actually does. Let's get back to our example we had, right? We said we wanted to compute pi, and we divided our computation into smaller pieces, into smaller tasks, where each of those tasks was computing a subregion of our integral. In this case, it was 4 subregions, and we had these 4 different codes we were running for each of those subregions that are just essentially different in terms of the boundaries of the iteration they do. So we have 4 sequential tasks. And what we were doing before, first we were running it sequentially. We had some sequential code that was running over the number of blocks and was invoking some function which we call pi helper, which receives the block boundaries from 2 and h as an argument, because we need h, the width of the blocks of the rectangles, to compute things. So that was a sequential code. Try to remember that sequential code, because you will see that the fully parallelized version using async looks almost identical to that. Just to remind you, that is a pi helper function which computes the sub-result for one of the blocks. For one of the subregions, it receives 3 arguments, begin and end of the iteration, and that double h, right? The begin of the iteration, the end of the iteration, and that width of the rectangles, just to remind ourselves. And please note, it really just computes that local pi and returns it in a normal way, as we expect it to do. So let's use async for the exact same thing. Well, we need a loop. We probably will get one future for each of those block results. So we create a vector of futures, and then we call async as many times as we have blocks by just passing along the very same arguments as we had before, right? The begin, the end, the age, and we use that very same pi helper function that we have just seen on the previous slide that was used in the sequential code, just in an asynchronous setting. Well, the only thing what we need to do, we need to wait for all the futures to be ready, right? So we have another loop which calls get on all the futures we created and accumulates the result in our pi, which we have locally here. Nice. No threads, full parallelism. The good thing also is that, as you already have seen, the pi helper function is not even aware that it's being launched possibly on a different thread. It's a normal function, which is the very same as you've been using in sequential execution. There's nothing special about it, which also tells you that, hey, there's no synchronization needed anymore. We don't have to synchronize in order to, well, because we don't have global data anymore. All the data is encapsulated in essentially represented by the future, because each of the futures receives its own sub-result for its block, and here we can just sequentially go over all the futures and accumulate the result locally without any threading issues, which is great. So why all tasks run in parallel? Well, as long as we have compute resources. The pi helper function has no awareness of the fact that it might run in a new thread. It's still a completely normal function. There's nothing special about it. It simply returns its calculated results. In that case, no synchronization is needed, which is great. And it is not too difficult to get from the sequential version to the parallel version. All you have to do, you add that async and that small change related to the futures, and you get a parallel version. Great. We will see how we further can simplify that and how the fully asynchronous code I will present to you next lecture essentially looks even more identical to the sequential code. So you don't have to turn your brain around in order to parallelize things. You take the sequential code, apply some very formal transformations to that sequential code, and you get parallelization. Full automatic parallelization under the hood. So just to prove that things are okay, here are a couple results. So I was invoking that with a different number of threads, from 1 to 8 threads. And since my laptop has only 4 cores, you see that it barely scales beyond 4 threads, obviously. Well, it has 8 hyperthreads, that's why there's a bit of speed up, but the actual speed up happens only up to 4 cores here. So in the end, for 4 threads, we get a speed up of about 3, which is kind of reasonable. And for a laptop that probably was checking for email in the meantime while I was running that benchmark, that's fairly okay. One side note I want to make is that standard async can potentially take an additional policy. And the standard defines 2 possible values for that launch policy. One is did launch async, the other one is still launch deferred. If you use did launch async, the task will be executed on a different thread. Whereas when you use did launch deferred, the task will be run inline in the calling thread at the point when you call get. So it will not run on a new thread. It will run only when you actually eventually call get. And while get is being invoked, the function will be run. So the task is executed on the calling thread the first time the result is requested. It's kind of lazy evaluation if you think about it. The problem, and that's the reason why I'm telling you that, is that if you use async without a launch policy, the standard says whatever. The system is free to use whatever it deems to be the right way to use, which might lead to the fact that it might actually decide to use deferred for the invocation. And that is not what you want, because if you use deferred, as you see, you have no scaling whatsoever. And that's obvious, right? Because if the function is executed while get is called, you sequentialize the execution of the tasks while you loop over all the futures. So be careful with that. Deferred can be a bummer, and it can cause you to get results that are unexpected. So my suggestion is, when you use std async, always supply the std launch async execution policy as a first argument, and then you're safe. Who knows these two people? Very famous people. Anybody? No? Everybody has seen the movie. Bonnie and Clyde, the bank robbers. You probably have heard of them. And I just want to sidestep from a moment to get away from the asynchronous part, because I realize that while we were talking about synchronization between threads, I missed to give you one important detail. And I want to come back to it just with 2-3 slides, and then I will go back to asynchronous computing. But anyway, Bonnie and Clyde, if you haven't seen the movie, just watch it. It's nice to watch. It's just sad that they die in the end, but okay, that's life, apparently. Okay, so let's say Bonnie and Clyde use an ATM and they want to rob the bank. So they have a bank balance of $300, and there's a main program which prints the starting balance and the final balance after all operations have been finished. It has two async operations where Clyde withdraws $100 and Bonnie withdraws $100. Then both wait for their money to be delivered to them. And just for completeness, here's the withdraw function. Where is it? Here. That is happening. So the withdraw function does two things. It stores the current bank balance. It prints whatever should be withdrawn. And then it computes a new bank balance. Well, you already see what's happening, right? It's Bonnie and Clyde, after all. So they rob a bank. So what will be printed? What do you think it will be printed here if both withdraw $100 using this code? Come on.
The F2, right?
What? Oh, well, both withdraw $100. What will be the final balance if the initial balance is $300? Huh?
It's $100.
Well, then it wouldn't be Bonnie and Clyde, right? They wouldn't rob the bank because the final balance is 200. As you might expect, well, race conditions, right? What we do is we first copy the current bank balance, then we print something which takes a half a second, and then we compute the new balance and write it back. And that withdraw function is run by two threads at the same time, concurrently. So both get $300 in and subtract $100 from it and overwrite it, and that gives you an overall balance of $200. Isn't that great? Wouldn't it great if banks would work that way? Sadly, they don't. Anyway, race condition. And I wanted to come back to it because what we have here is we have two different things we want to protect from arrays. We want to protect the print function from arrays, because if two threads start printing at the same time to the console, the two outputs get scrambled. They are overlapping, so you get some gibberish. So you don't get the thing you need. So what we want to have is two mutices. One mutex for the printing operation and one mutex for the actual bank balance computation. What happens when you have two mutices that are being acquired in different places, and you always have to acquire both mutices in order to make the operation correct? Well, what you want to do, you want to make sure that these mutices are acquired in the same order. Because if one thread acquires mutex A first and then mutex B, and the other thread acquires mutex B first and then mutex A, you might run into a deadlock, because while one thread acquired A and the other thread acquired B, then none of the two threads can make progress because the other thread already has acquired the other mutex. So you want to ensure that muteces are always acquired in the same order. And that is what I want to talk about and introduce you to, because I mentioned it but never explained it. The C++ standard has a facility which is called standard lock, where you pass in an arbitrary amount of muteces, and it will internally make sure that the muteces are acquired in the same order always. So standard lock will acquire these two muteces, which makes that operation safe afterwards and lock-free, deadlock-free. But the other problem is that we always said that we shouldn't use lock directly and lock and unlock directly, because what we want is that at the closing brace, the muteces are being given back, are being released automatically. But lock only locks the two muteces. It doesn't give them back. It doesn't unlock them when it goes out of scope, because lock is a function. It's not an object, it's a function. So we need to do additional things in order to make sure that our muteces are being unlocked at the end of the scope, which we can do with a normal lock guard, but with an additional argument which tells it, hey, take over the lock that mutex already has, acquire it, adopt it. And then this message lock will own the mutex and will release it when it's being destroyed. We do the same with the other one. The ATM mutex is acquired in the same way, and that makes sure that in the end of the block, both muteces will be released, which is what we need. Okay? So the idea is, and that's the whole reason why I'm doing that sidestepping from the asynchronous computing to Bonnie and Clyde, is I wanted to give you a way or explain how you can use the lock facilities together with the lock guard or with the unique lock facilities we have in your code and ensure that it's deadlock free. That's the whole purpose of this exercise. Any questions about that? Yes?
What the message log we had until the scope?
Well, the message log goes out of scope here. And that's it. Well, you could make it go out of scope here by just putting another block around it if you wanted for it to go out of scope. Yes, sure, that would work. Other questions? Okay. Well, then let's go back to the future. What ways do we have to create a future? We have seen one. We have seen async, and I will show you more about that. But the standard gives you two more ways to create a future. One is called the package task, and the last one is called the promise. And I will introduce these things to you just to give you a bit more understanding what the standard actually provides. But unfortunately, standard future, the future as specified in C++11, between you and me, don't quote me on that, is completely useless. Because, well, almost useless. You can't do a lot with it because it doesn't have any facilities that you can combine several futures. There are many things that are missing from the standard, how it's been defined in the standard. So what we have done in HPX, there are many more ways to create one and many more ways how to operate with futures, which actually makes that asynchronous programming model I'm talking about possible. So, but let's talk about these first to give you some impression on how does it actually work under the hood. Let's start with a promise. That promise is a type that is the main maker of a future. It's always used whenever you need a future, even if it's somehow hidden behind the scenes. So it gives away a future representing the value it receives. And you can think of a promise and a future as being a one-shot pipeline that receives the value, the promise receives the value, and the future can extract the value out of that pipeline. It's a one-shot pipeline. You can use it once only. So every promise gives you the future once, and you can use it once to transfer information from the promise to the future. So it's somehow an anonymous connection between a producer and a consumer, where the producer sets a value in the promise, and magically the same value appears on the other end of the pipeline, which is represented by the future. This is implemented by the promise creating what's called a shared state. A shared state is a third object that is somehow in the mix. And that shared state actually stores the value. And both future and promise are connected to that shared state so that they can communicate. So this is a shared state that actually stores the value. You have a promise which creates a shared state. And whenever you request the future from the promise, the future will be connected to the shared state as well. So that if somebody sets the value on the promise, somebody else can get the value from the shared state. Futures are created by the promises, as I said. Promises have a member function which is called getFuture. So it gives you a future. The promise has another member function which is called setValue, which receives the value. So whenever somebody wants to use that pipeline, you call setValue with the value you want to store. And f.get will retrieve the value from that shared state, which lives underneath, hidden behind the scenes. So you will never see the shared state in any way. I'm just showing you so that you understand how is that mechanism actually working. The good thing about that scheme is that promises and futures are completely thread safe. You don't have to worry about thread safety issues when you're using promises and futures. So you can share promises and futures between threads, no problem. You can access promises and futures from different threads at the same time. It's guaranteed to be thread safe, so you don't have to worry about these things. Okay, let's implement async using that knowledge we have. Let's implement our own async. How does it look like? Well, we know async returns the future, and the future, the template argument to the future is that complicated looking constructs std invoke result t, which essentially computes the result of the function f when it's being invoked with the arguments. So it's a compile time way to figuring out what is that function returning. Is it an int? Is it a double? What is it? And since the return future I have to represent the result f is actually returning, we have to use that magic facility that gives us the result. Okay, so as I said, we create a promise. The promise has to represent the very same type. It stores the very same type. Then we ask the promise to give us a future. Give me the future. So at that point, I split the promise apart into two pieces, and I have a promise and a future that both refer to that anonymous connection that are connected through the shared state. And last but not least, I create a thread, which I pass a lambda to the thread. And that thread, when it's executed, calls our given function, f, with the arguments. And whatever f returns is used to call the set value on the promise. Right? So this is where the magic happens. We create a new thread, which runs the function, and whatever the function returns is passed to the promise that we have created. And since we pass it to the promise, that future will eventually receive it, because at this point we have given away the promise to the other thread, and the future stays with us. So we hand it away to another location in our code. The only thing that's missing here is we have to detach the thread object from the physical kernel thread, because we want for the thread to keep running when we return from the function, from the async function. So we have to decouple the physical thread and the operating system from our thread object we have created here, which we do with thread detach. And that's it. That is how async is implemented. Well, without the launch policy, obviously. You can look at the code in your standard library. You will see something very, very similar. That is what's happening in async. And that makes you understand that how async actually works, because it creates a new thread, runs the function I provided with, passes the arguments along I provide to it, and uses whatever f returns as the value that is passed to the promise. And whoever receives the future that comes back from async can call get on the future and will receive whatever that function has returned and whatever was passed to the promise. Now we can show another example of how to use that wait function I was mentioning. So let's have some simple code which creates a promise, which gets a future from the promise. It creates a thread which sleeps for 5 seconds and then sets a value on the promise. Just for simplicity, I wanted to have some very simple example that is easy to understand. And we have a loop that attempts to wait for the future for 1 second repeatedly. So the first time it will probably time out, the second time it will probably time out, and so on and so on. And after the 5th attempt, it will probably give you the result, right? Because that thread has waited for 5 seconds, then it set the value. So after 5 seconds, this wait for will not return timeout anymore. It will return something else. I forgot. But it will not be timeout because the value has been available. And at that point, we can print the result. So the whole program will probably print something like this. It will attempt to wait for several times, 1 second apiece, and eventually it will get the result. So you see how you can use wait for to wait for the future. Well, we're all waiting for the future in some way, right? But wait for this future and ask it to time out if the wait is taking too long. Just as a very small example. Okay. The second way to get a future from the standard library is to use package task. Package task is a function object. It's a function. And that function gives you the future for its result right away. The nice thing about that is that you can pass a package task to a callback interface. If you have some system that you give it a function which will be invoked once the I/O has happened, or when the mouse was moved, or whatever, some event-driven system where you give a function to the system and the system invokes that function when some event happens. Now, normally that function is just invoked, but sometimes you want to get a future from that. You want to get a future when you register a callback with one of those APIs. And at that point, package task is exactly what we want. So in a simple example, I create a package task which encapsulates a function that computes the power of the 2 arguments. Please note that package task has a very strange syntax of specifying what function it can encapsulate. And this means that package task can represent any function that returns 1 int and takes 2 arguments that are integers as well. So while that looks a bit strange, it's essentially like the function signature. You can think of that way. So this package task can be initialized from any function that has that prototype. Well, our Lambda has that prototype, right? It takes 2 integers and returns an integer itself, so you can bind it to that package task. Now we ask the task for, hey, give me the future. That future returned from the package task will become ready whenever that function was invoked. Doesn't matter in what context. By another thread, directly in line, like I'm doing it here. So if I'm invoking the package task with 2 arguments, that result will be passed to the future. And we can call get on the future, and we will get our result, which is 512 in this case, because we wanted to compute 2 to the power of 9, right? Very simple example. But as you see, once you have a package task, you can pass it to any context where it will be invoked. Yes?
What happens if you call the function twice?
No, it's once.
What happens if you call it twice?
Well, as I said, futures are one-shot. A package task encapsulates a promise to create a future. This is a one-shot pipeline. So when you call it again, you will probably get an exception. It will complain about it. It will probably tell you that the future has already been initialized or something like that. So you can call it once. It's a one-shot thing. How is that implemented? Just for the curious of you, it's not difficult. A package task combines 2 things: the function it wants to invoke and a promise, which will be used to set the value. It has 3 functions: the constructor, which stores the function, the function operator which will be invoked when I invoke that thing with some arguments, which does nothing more than calling our function with the arguments and uses a return value to set it in a promise. And the get future on the package task just asks the underlying promise to give it the future. So again, promise is used as a main implementation technique to make all of that happen. Again, it might be a bit surprising, syntax, and this is a template syntax we have not seen yet. Don't worry about it. It's the way you have to implement it in C++. If you're interested more about these techniques, I can certainly talk about it. But for now, just take it as is and ask questions afterwards, okay? Good. So that's how you build a package task. Last, and then I'll let you go. Let's implement async using a package task. Why not? Same interface again. But this time, instead of creating a promise directly, we create a package task, ask the package task for its future, pass the package task as a thing that the thread is executing, as a function the thread will be executing, detach the thread, and the rest is absolutely the same as before. So just as an example, as you can see, package task can not only be invoked directly, you can pass it to any object or to any function in the C++ realm that expects you to pass a function. And since package task is a function object, you can do that. Okay. Any questions so far? Then let's do some conclusions, at least for today's lecture. When you write code, and that's a general rule, which probably is obvious and nothing new for today's lecture, but I want to repeat it anyway. If you write code, always assume that somebody in the future might want to use your code in a parallel environment. Using context-free functions, like I used with a PyHelper, so functions that don't operate on global variables, but are completely self-contained, receive all values they need for the computation and return the value they computed. Using those context-free side effect-free functions are always a good idea because they prevent multi-threading issues by design. If you do that, there can't be any multi-threading issues. Well, avoid data races. That's one of the techniques you can apply. Minimize explicit sharing of writable data. Again, same thing. So think in terms of tasks rather than threads. So async is really your friend. Start using it wherever you can. Use the scheme we used for locking, unlocking. Use the constructor to do some operation and use the destructor to do the opposite operation, be it locking of a mutex, be it opening of a file, which is closed automatically when the file object goes out of scope, and so on and so on. C++ people tend to invent strange names. RAII stands for resource acquisition is initialization, which doesn't tell you anything. But what it stands for is use the constructor to initialize something and use the destructor to do the opposite thing. Standard vector allocates memory in the constructor and deallocates things automatically in the destructor. File fstream opens the file in the constructor and closes it when the destructor is called without you having to call close. Lockguard locks the mutex in its constructor and unlocks the mutex in its destructor, and so on and so on. So it's a very powerful technique, and C++ is the only language, almost the only widespread used language that allows you to do that. And that's the reason why I'm telling you the destructor is the most important feature C++ has, because it allows us to do these things. It allows us to write code that cleans up after itself without you having to do anything. Use standard lock when you have to acquire multiple mutices, and use std launch async when using std async. That's, I think, what we learned today. Any questions so far? Yes?
Since we had two locks and both of them were going out of the scope at the same point, do we really need two locks?
Well, I wanted to construct a contrive example that requires two locks. In that case, we might have gotten away with one. But I wanted to have one log for the printing operation and one log, because in other contexts of your program, you might just print without doing anything. So you might want to acquire just that log without hindering the other operation to go forward. Yeah? Other questions? Okay, well, thanks for today and see you on Thursday. And Thursday will be really interesting, and be prepared for some mind-bending acrobatics in terms of how to write code. But it will resolve to a very nice solution in the end. Okay, see you on Thursday.